to start. So good afternoon, everyone. Welcome to this second installment of our August mini school on the modeling of optical spectra. Like last week, the lecturer for this week is Professor Tjaart Krüger from the University of Pretoria. And Tjaart, I introduced you last week, so I don't have to introduce you again, because I think that the audience is the same. So Tjaart, I won't eat up in your precious time. So you're welcome to start your presentation. I just give the usual reminder to the participants, please use the Q&A to ask questions. And at the end of the talk, if you raise your hand, we can give you the speaking rights to ask your question in person. We are not so many, so we can easily do that. Yeah. Okay, Tjaart, please, over to you.
Thank you very much, Francisco. Francisco, is this lecture being recorded?
Yes, it is. You should see on the top right corner of your Zoom screen, there is a recording in progress thing.
Okay, perfect. Yeah, I've hidden the floating panels. So just wanted to make sure.
No. It's been recorded. It's like all the lectures that we do. Perfect. So thank you, Tjaart. Over to you.
Yes. Okay. Thank you very much, Francisco, again for this kind introduction. So this is the second lecture of a series of 4 lectures on modeling of optical spectra. And last week, in the first lecture, I have focused on the basics of light-matter interaction. This lecture is going to build on the material of last week's lecture. I'm going to focus on coupled molecular dipoles in the context of light-matter interaction, and then specifically look at strong interactions, which gives rise to molecular excitons, and weak interactions, which gives rise to Forster type of interactions. Okay, so again, the outline of the 4 lectures last week was focused on the basic principles of electronic spectroscopy. This week, I'm looking at coupled molecular dipoles, and these 2 lectures are again setting the stage to take this topic further and focus in the next 2 weeks specifically on linear and nonlinear spectroscopy, so ways to model linear and nonlinear spectra, and then also excitation energy transfer in the strong coupling limit. So I'm going to focus mostly on, after building the theory, I'm going to focus on excitation energy transfer in the weak coupling limit. So this is the Forster regime. Next week, we are going to focus more on the strong coupling limit, and that's going to be given by Dr. Towan Nöthling. Right, the outline of this lecture is given as follows. I'm first going to focus on intermolecular interactions, and then focus mainly on dipole type of interactions, and then specifically transition dipole interactions, and that will then lead to the excitonically coupled dimer. And then I'll look at 2 very specific types of dimers, which are called H and J aggregates. And then finally, I'm going to look at the weak coupling regime, which gives rise to Forster resonance energy transfer, and also do all the appropriate derivations along the way. Okay, so let's start with intermolecular interactions. The starting point is again electrostatics, and we are considering a molecule's electron cloud with a continuous volume charge density rho at position vector r prime, which generates an electrostatic scalar potential at r. Okay, so here's our molecule, and let me just hide this panel. Okay, so we are considering the electrostatic scalar potential at this position vector r. Okay, and this is being generated by the charge density of this molecule. Right, so we can write our scalar potential in terms of the charge density like this, and the corresponding electric field is given by the Poisson equation, also the one which we have used last time. So now we can Taylor expand this 1 over the difference between the 2 position vectors that we are considering. We expand this around r prime equals to 0, so around the origin of our coordinate system, and here are the different terms of our Taylor expansion. And this is obviously only applicable when our position is much further away, well, is far enough away that we can say this position vector of the molecule if we can approximate it with a sphere. Okay, we can now expand our scalar potential into multiple moments by substituting this expression into the one up here. Okay, so this is what we then get, and all these different terms are then related to the different multiple moments of a charge distribution. So the first term, Q here, gives us the electric monopole, and this is the case when we have a charged molecule with an electric charge, Q. The second term is related to the electric dipole. So if we are dealing with a permanent dipole, then this is the relationship between an electric dipole and the charge density, and then we get the electric quadrupole term, and so we can go to higher order terms. Okay, so this slide is very similar to what was also presented in the first lecture. Now we are going to approach it slightly differently. In the first lecture, we considered the interaction between a charge density of some molecule and an incident electric field. Okay, so instead of this scalar potential, we considered the electric field that interacted with some charge density. In this case, we are now going to place a second molecule with charge density ρ2 at R. Okay, so this is our setup. We have a molecule 1 with charge density ρ1 and scalar potential at position vector R, and then exactly at this position we are going to place our second molecule 2. Okay, so now since molecule 1 generates the scalar potential, this scalar potential and the charge density of molecule 2 are going to interact. And the interaction energy, or the potential energy of this interaction, is given by this. Okay. So this is only one part of the interaction, because molecule 2 also has a charge density, ρ2, at this position. In other words, because of this charge density, it also generates a scalar potential by 2. Okay, and this scalar potential reaches molecule 1 and interacts with the charge density of molecule 1. Okay, so this interaction works in both ways. So we can state it like this, but now we are starting at this position and we have to get back to molecule 1. So we are working with negative R, okay, starting here and working backwards. So molecules 1's center of mass is at negative R with respect to molecule 2. In other words, we must consider this charge density interacting with this potential. Okay, and the resulting potential energy is then given by this. Okay, so the total interaction energy is the sum of these two. And if we again divide this into all the multiple moments, we are getting all these terms. Okay, so the total electrostatic potential energy is given by this equation. The first term here is the Coulomb interaction. If we have two charges that are interacting, that is going to give us the Coulomb potential energy in this case. The second term gives us the difference between the interaction between a charged molecule and a permanent dipole, and a charge of molecule 2 and permanent dipole of molecule 1. The third term gives us the dipole-dipole interaction. The fourth term gives us the interaction due to charge 1 and quadrupole 2. Yeah, and also vice versa, and we can continue with the higher order terms. Okay, so let's summarize it in this slide. So if we have two charge distributions, ρ1 and ρ2, they interact with the Coulomb potential given here. So we have the double integral that we have to integrate over. So for each molecule, we can calculate the following: the total charge, which is given by this, the dipole moment given by this, the quadrupole tensor given by this, and so on to higher order terms. And to put everything together, here is our single equation combining all these different terms. So in general, we are considering non-charged molecules. And in that case, all these terms become zero because Q1 and Q2 being permanent charges, and only this third term remains. But this is the case for permanent dipoles. However, as we have seen last week, we can use exactly the same expressions which we get from electrostatics and then exchange the permanent dipoles to transient dipoles. And this transient dipole is a transition dipole moment, which results from the interaction between the electric field of the incident light or the electromagnetic wave, so electric field of the electromagnetic wave, and the charge density of our molecule. Okay, so in other words, we can replace all these terms with our transient or transition dipole moment. Okay, and now the dipole approximation for uncharged molecules. Okay, we get this potential energy that arises from the interaction between our electric field and dipole, which is given by this. Okay, so this is now the potential that will determine what is the probability of transitioning from this state, initial state, to the final state. And we can put everything together in terms of the transition dipole moments. Okay, so this is what we are going to consider. And something else to note, since we are dealing with transition dipole moments, actually two coupled transition dipole moments, this coupling also determines the transfer of energy from one molecule to the other one. Okay, so as soon as we have developed the theory that describes the interaction, we can immediately continue to describe the theory underlying the energy transfer. Okay, so let's have a look at the underlying theory of two coupled dipoles. So we are going to call this an excitonically coupled dimer. And we consider two spatially separated interacting molecular dipoles. Let's consider that each molecule has its own set of electronic states and energy levels. And now in the absence of interaction between the two dipoles, the solutions of each dipole separately is satisfying the time-independent Schrödinger equation. So this is now in the absence of interactions. Okay, and yeah, n is now set equal to 1 and 2, and I denotes the electronic state, so either the ground state, first excited state, or higher states. Okay, so using this notation, we can consider any number of interacting dipoles and any number of electronic states that are involved. But let's, for the sake of simplicity, just consider the simplest case, which is a two-level system. We consider ground state when I is equal to 0, and first electronic excited state when I is equal to 1. Okay, so this is our energy diagram. We have molecule 1 with ground state energy given here, electronic excited state given by epsilon 1, 1. And then we have molecule 2 with ground state energy there and first electronic excited state given there. And we are considering the interaction between these two. Okay, so because of this interaction between the two dipoles, we consider them as a single system. Okay, we call this the dimer. Okay, so in other words, we have to work with joint quantum states as well. So our ground state wave function is now going to be given by this product between the individual monomeric wave functions. And the ground state energy, okay, this is going to be given by the sum of the individual Hamiltonians acting on our state, or, well, transforming our ground state, and the system remains in the ground state, so just one of the diagonal components, if one considers that. Okay, and we also incorporate the potential, interaction potential between the two dipoles. Okay, so the first Hamiltonian, okay, well, it's basically the expectation value in the ground state, so that gives us the ground state energy of molecule 1. Expectation value of second Hamiltonian gives us the ground state energy of molecule 2, and then we have this interaction term. Okay, so we use a notation V00, which means that, well, in most cases, this V00 is not 0, which means that the energy, the ground state energy of our dimer is shifted with respect to the energy of our two individual molecules. Okay, let's now consider the excited state wave function. So because we are considering joint states, there are two options. In the first case, molecule 1 is excited and molecule 2 is in the ground state. In the second option, molecule 1 is in the ground state, molecule 2 is excited. Okay, and we have to consider a linear combination between these two possible states. Right, the associated excited dimer Schrödinger equation is then given by this. So this excited state wave function must be a stationary solution of this Schrödinger equation with corresponding eigenenergies. Okay, and this is what we are going to solve now. Okay, we can solve this by means of time-independent perturbation theory. So this interaction potential is generating a perturbation, and we can in fact consider degenerate perturbation theory. And that is easiest seen by considering two identical dipoles. Then the energies are going to be degenerate, and then it makes sense to use degenerate perturbation theory. But even if the energies are slightly different, it is still very useful to use degenerate perturbation theory. Okay, so that's a framework that we are going to use, time-independent degenerate perturbation theory. Right, so the non-trivial solutions of our Schrödinger equation are given here. Okay, where this is just a shorthand notation for all these terms. Okay, and if you are used to the so-called W matrix in degenerate perturbation theory, we can then write our states, our joint states like this. Say this is phi A, where molecule 1 is excited, and phi B, where molecule 2 is excited. So our W matrix is going to consist of these components consisting of phi A and phi B in all the different combinations. Okay, these two terms are the resonance interaction terms. The first two terms are just the diagonals of your W matrix. These two terms are the off-diagonal components. So they relate to resonances between the two states. So if you inspect this state, what's happening here is that this perturbation or this potential is transforming this state, so the ket, into the bra. Okay, so it's transforming a state where molecule 1 is excited into a state where molecule 2 is excited and molecule 1 is in ground state. Okay, so in other words, this is a form of, can say, energy transfer from molecule 1 to molecule 2. And V21 is just the other way around. So transforming the state where molecule 2 is in the excited state to the state where molecule 1 is in the excited state. Okay, so resonance interaction terms. So if we would add a time dependence, what's going to happen is because of these resonance interactions, this system is going to fluctuate or oscillate between these two states. Okay, and it's going to oscillate forever if there's no energy sink or no interaction with the environment, for example, other molecules to which the energy can be transferred. Okay, let's now consider identical molecules. So in that case, the ground state energies are 0. The first electronic excited state, the energies are also equal. V12 is equal to V21, and V11 is also equal to V22. Okay, so related to the site energies on the diagonal. Okay, so then this determinant reduces to this form, and we can easily calculate the associated energies of our dimer. Okay, and there are two different energies. Okay, so if we would sketch this, okay, here we have the individual molecules that are interacting. Okay, and the dimer system, or our excitonically coupled dimer. Okay, you see here, as I've explained on the previous slide, that the ground state energy is shifted with respect to the energy of the individual molecules. And then because of V11, the average of the two different excited states of our dimer is also shifted, V11. Okay, and we have two different energies. So we have a splitting of energies, plus and minus V12. So the energy difference between the two different resulting energies is equal to 2 times V12. Okay, so this is called the, well, Davidoff splitting or excitonic splitting in such an excitonically coupled dimer. Right, so we have two different energies. Okay, where as we started in this specific case with degenerate energies, the energy levels are split. And if we look at the wave function, there are also two associated wave functions. Of course, if you have two solutions, so two energies, you also have two associated states. Okay, so we here have a plus and a minus sign, and this can be visualized or actually described in terms of oscillations, or visualized in terms of coupled pendulums. So the plus sign would relate to a state where you have two pendulums that are oscillating exactly in phase, and the minus sign corresponds to the opposites symmetry. So two pendulums that are oscillating exactly out of phase. Okay, so now our excitonic wave function, or our dimeric wave function, is a superposition of the two possibilities. Okay, so let's have a closer look at these wave functions. Yeah, and before we do that, just a different notation that I'm also going to use later on. So if we use this notation, yeah, so this is equivalent to this notation, where molecule 1 is in the excited state, molecule 2 is in the ground state, and here molecule 1 is in the ground state and molecule 2 in the excited state. Okay, let's now look at optical transitions. Okay, so in this case, we are considering our transition dipole moment, okay, which is related to the transition from this state. So say our ground state to the excited state here. Or our, well, state 1 of our coupled system to state 2 of our coupled system. This is our transition dipole moment. Dipole strength is something that I haven't introduced in the first lecture, but it's very useful in a context of optical transition. So dipole strength is simply the modulus squared of the transition dipole moment. Okay, so this is, as you would expect, directly related to all the other probabilities that we have worked out in the first lecture. For example, the Einstein coefficients, the probability of transitions, the absorption, cross-section, extinction coefficients, all of these. Okay, so this is a probability indicating the transition from state 1 to state 2. Okay, and it can be written like this if we have the units of Coulomb meter squared. Okay, epsilon here is again the extinction coefficient, which we are expressing in terms of the angular frequency. Okay, the excitonic transitions and dipole strengths depend on the structure of the dimer. Okay, so that means the relative orientation between the different dipoles. Let's consider, for the sake of simplicity, isoenergetic molecules. In that case, we have the two different states, each with its own dipole strength. Okay, so if we consider the separate transition dipole moments, mu1 and mu2, interacting with our joint state here. So this is where our dimer, so both molecules are in the ground state. Okay, and because of the excitonic coupling, we have then two excited states. Okay, and they are related to the dipole strength, which we can write like this. So for two identical molecules, we have a prefactor here, it's the dipole strength times 1 plus or minus cos theta. Theta here is the angle between the two dipoles, mu1 and mu2. Okay, let's consider two anti-parallel dipoles. So it's a case like this where theta is 180 degrees. So cos theta is going to be equal to -1. And then our two dipole strengths are then 0 and 2 times d01. Okay, so in the first case, no absorption occurs to the first level. So this is the transition from the ground state to the first excitonic state. If the dipole strength is 0, it means that there's no oscillator strength. And that is because of the anti-parallel dipoles. So the dipole moments are going to cancel out completely. So they are exactly out of phase. So they will cancel each other out. No oscillator strength, no absorption from the ground state to the first exciton level. But D2 has all the oscillator strength. So all the oscillator strength is now accumulated in the transition from the ground state to the second level. Okay, and this brings me to this very interesting topic of parallel dipoles, where we are considering two types. So let's first consider again the dipole-dipole approximation for uncharged molecules. So we have our interaction potential due to the light-matter interaction. So we are considering the transition-dipole interaction, which is given by this term here on the right. For parallel identical dipoles, this interaction potential can be reduced to this form. Okay, where theta now is this angle between the direction of the dipoles and the position vector connecting their midpoints. Okay, so if we consider again, our two monomers that are coupling to form the dimer, then we can consider two types of, let's start with two types of orientations, two geometries. Orientations, both cases they are parallel, but just two geometries. And the one is the head-to-tail arrangement on the left, and the other one is the sandwich configuration. Okay, so in this head-to-tail configuration, the transition from the ground state to the second excited state, or second exciton state, is completely forbidden, and all the oscillator strength is in the transition to the first exciton state. For the sandwich configuration, it's just the other way around. And the way to understand this is given here on the next slide. But yeah, before I get there, so if we consider this angle theta and plug it in for these two configurations, you get theta equals to 0 and theta equals to 90 degrees. So that gives you the interaction potentials V12 for these two cases. So in this case, we have a negative potential. In that case, we have a positive potential. Okay, so let's have a look at a more general case of theta, and we differentiate between two types of coupled dimers, or also called molecular aggregates, or parallel dipoles. One is called a J aggregate, and that is a case when this theta is smaller than the so-called magic angle. The magic angle is the angle where cos squared theta is equal to 0. So in other words, this interaction potential is going to be equal to 0. So in other words, if this angle theta is smaller than 0, you will get a potential that we have seen here, negative potential. In the case of an H aggregate, the angle is greater than the magic angle, and obviously smaller than 90 degrees. And we have the case with potential here positive. Okay, so for the J aggregate, we have negative potential, H aggregate a positive potential, and J aggregate doesn't necessarily have to be a head-to-tail orientation like this. It's just a case where theta is smaller than the magic angle. Theta smaller than the magic angle. Okay, so here are again our split exciton states, so exciton splitting. We have the case for the J aggregate and the H aggregate. Okay, here are shown the two different joint states, the two possible states where molecule 1 is in the excited state, molecule 2 in the ground state. Here's the case where molecule 1 is in the ground state, molecule 2 in the excited state. And here we have our two dimeric states, where you can see in this case the two dipoles are parallel, or they are exactly in phase, and that is again given by the plus sign. And for this upper state, we have the two dipoles being out of phase. So in other words, they are oriented at every time opposite to each other, exactly out of phase. And the result is, if you get two identical dipoles, the net dipole moment is going to be 0, and the net dipole moment of this transition, or the net transition dipole moment, is going to be square root of 2 times the individual dipole moments. And for this reason, the lowest state contains all the oscillator strength, so that is the optically allowed transition, and the transition to this second state is going to be symmetry forbidden. In the case of the H aggregate, it's just the other way around. So now the lower state is the antisymmetric state, where the two dipoles are out of phase, and because of this symmetry, again, the two dipoles out of phase, they are going to cancel each other out, so the net dipole moment is going to be 0. So this will be an optically forbidden transition, and the transition to the second exciton state is going to be optically allowed. Okay, so this primary difference between the J and the H aggregates related to which of these transitions is allowed and which is forbidden has dramatic consequences in terms of spectroscopy. Okay, before I show a few examples, let's briefly revise the Frank-Condon principle, which I introduced in the previous lecture. Okay, so we are considering a scenario like this. We have the ground electronic energy potential and all the different vibrational states that are accompanying this ground state potential, and the same for the first excited or first electronic excited state. Okay, so as I showed in the previous lecture, the dipole moment that's connecting the initial state, ground, it can be the ground state, to the final state, which can be excited state, or the other way around for fluorescence, is given by this. Okay, where we have the different electronic energy levels, the vibrational levels, and the spin states. Okay, so the transition probability is dictated by, firstly, the Frank-Condon factor, which is the modulus squared of this term in red. And then there are also symmetry considerations that we have to take into account. So firstly, Laporte's orbital selection rules, which I'm not going to go into detail, and then also phase relationship between multiple dipoles, which I've illustrated in the previous slide. If they're exactly out of phase, you have no dipole strength. If they're in phase, you get an enhancement, which is also called superradiance. Okay, and then we also have the spin selection rules, and that depends on the multiplicity. So, yeah, these transitions must be to a state with the same spin multiplicity. For example, if you start in a singlet state with a total spin of 0, then the transition must be also to a singlet state. Okay, these two symmetries, or these two selection rules can be broken by perturbations. In the case of spin selection rules, you can have spin orbit coupling that can allow a transition from, for example, a singlet state to a triplet state. But the same applies to these different symmetry considerations. So I'm going to show a few examples of that in the next few slides. Let's also consider again this mirror symmetry between absorption and fluorescence. For example, if you consider this transition from the, and this is the typical notation that is used, just showing the vibrational levels from the ground state to the other electronic state, normally the first electronic excited state. So this 0 will relate to the vibrationless ground electronic state, so with nu double prime equals to 0, and the transition is to the 6th vibrational state in this first electronic excited state. So it will be exactly this purplish arrow that is seen here. But the probability for this transition is the same as the transition from 0. Okay, so the vibrationless ground, or say, yeah, well, the ground vibrational state, so that's a vibrationless electronic state, first electronic state here, to the 6th vibrational state in the ground electronic state. Okay, so let's have a look at some symmetry breaking perturbations. So let's consider this energy level diagram. So I've shown here the ground electronic state, first electronic excited state, second electronic excited state with some vibrational levels. Let's consider absorption first. So in the case of an H aggregate, we know that this transition is 0, and this is 0 for all transitions regardless of the vibrational state. So let's just consider this 0-0 transition. But just as this 0-0 transition is symmetry forbidden, the 0-1, 0-2, and so on will similarly be forbidden because we are dealing with here with the electronic states. Okay, now due to structural disorder, if we consider an H aggregate, structural disorder is going to introduce some tangential components, and that is going to make this transition allowed. And now the higher the temperature, the more structural disorder there can be in a material or in any system with coupled dimers. So one would expect that as the temperature increases, the probability for this transition also increases. So in other words, the intensity of the 0-0 transition increases with temperature. Secondly, interestingly, this transition, or from this transition upwards, so the 0-1 transition, even more with, is the case with the 0-2 transition, even more 0-3 transition, they all mix with the second electronic excited state. The 0-0, or this 1-0 state is typically too far from this electronic excited state that there's no mixing occurring. But generally there's mixing that occurs between the 0-1, sorry, not the 0-1 state, well, that's a transition, and well, the 1-1 state and the 2-0 state. Okay, so in other words, this would lead to a 0-1 sideband in a spectrum that is measured, and also a blue shift, normally a very small blue shift. Okay, typically these calculations consider the so-called Wang-Rice factor, which gives you the ratio between the intensity of the 0-1 transition to the 0-0 transition. And another way to define the Wang-Rice factor is it is a measure of exciton or electron phonon coupling. So coupling with vibrational modes of the molecule itself or some specific vibrational modes in the environment. Okay, so that gives rise to the Wang-Rice factor, which can enable a transition, or it can also reduce the efficiency of a transition. Okay, the same perturbations that I've spoken about here, so the structural disorder and also mixing with high electronic states, they also apply to fluorescence. And in fact, the effect of disorder specifically is strongly enhanced because of Kasha's rule. So Kasha's rule, he was the first person who noticed that most of the fluorescence takes place from the lowest vibrational state. So from this 1-0 state, that's where most of the fluorescence is going to take place from. Okay, so if we consider the electronic energy level for fluorescence and consider the transitions, again, due to the same symmetry considerations, the 0-0 transition is forbidden, but the 0-1 transition is going to be allowed, also due to coupling with high electronic states. Okay, it's also of note that the structural disorder affects mostly the 0-0 transition and not the 0-1 transition. So this Wang-Rice factor is then also a good measure for the structural disorder in the system. Okay, so there are different ways in which aggregate types can be determined based on the differences between H and J aggregates. Okay, so firstly, one can look at temperature-dependent absorption, or specifically fluorescence spectral evolution. So how the spectrum changes as a function of temperature. We know that this intensity is going to increase. There's also going to be either a blue shift or a red shift. And secondly, because this transition is optically forbidden, it has a very long fluorescence lifetime. Well, actually, if it's forbidden, then obviously there will be no fluorescence. But if there's any perturbation that gives rise to some allowed transition, that corresponding lifetime of the fluorescence is going to be very long compared to the case of J aggregates where this transition is symmetry allowed. Okay, and then the quantum yield of fluorescence is also very low. In the case of an ideal H aggregate, a perfect aggregate in the absence of any disorder or other perturbations, obviously there's no fluorescence, but as soon as you get some perturbation, some optically allowed transition taking place, the quantum yield for that is still going to be very low. Okay, one can do a Frank Condon analysis of the photoluminescence spectra. And this is just an empirical way of modeling, or actually more fitting experimental spectra. So in the case of J aggregates, okay, one considers some prefactor exponential function, and then the convolution of different vibronic bands. Okay, so each M here refers to another vibronic transition that is considered. Okay, so yeah, depending on how the experimental spectra look, how they are resolved, one would then consider a number of bands that are included. Gamma here is a Gaussian line shape. So just to take into account the line broadening. Yeah, so this is the case for the J aggregates. For H aggregates, there's another factor that has to be taken into account, and this is the so-called exciton coherence number, which for which we also multiply a Gaussian function with, so a Gaussian envelope for this exciton coherence number. And now, because we are considering H aggregates, because of the specific interactions, molecular interactions that are at stake in this case, generally pi interactions. So we consider pi stacking, and when there's no disorder, so in the case when alpha is equal to 0, there's very strong exciton delocalization along the pi stack. Okay, and that leads to spectral line broadening and also blue shift in the fluorescence spectra. Okay, as the temperature increases, the system becomes more disordered, and the exciton delocalization length correspondingly decreases. So in the case of alpha equals to 1, we have complete exciton localization. So we have spectral line narrowing and a redshift of the fluorescence spectra. Okay, so let's take all these differences between the J and the H aggregates into account. And this was a study that I did collaboration with the team at Addis Ababa University under guidance of Niwe Degagne, study that was published last year on this specific polymer, which is called the benzodiethiophene isoindigo copolymer. And we considered all these three different ways to distinguish between H and J aggregates in the system. Okay, so here are some experimental spectra that are fitted with Gaussian functions, and one can see the dominant band corresponding to the 0-0 transition, and also some side bands. These side bands are due to the presence of, well, obviously J aggregates where this 0-0 transition is the dominant transition, and obviously transitions between other vibrational states are also taking place. But some part of this can also be due to the perturbation that's causing H aggregates due to the mixing with high electronic excited states. Okay, of most interest here is to follow the spectra as a function of temperature. And the first observation we can make is that the intensity increases with temperature. As I've noted before, the intensity increase relates to the presence of H aggregates, because this lowest energy transition, which is normally symmetry forbidden, becomes more and more allowed as the temperature and hence also the disorder increases. Okay, if we express this in terms of the Wang-Rice factor, so the 0-1 transition is not very much affected by temperature. However, 0-0 transition is, we would expect a decrease of the Wang-Rice factor as a function of temperature, and that's indeed the case, which also points to the presence of H aggregates. Okay, secondly, there was a redshift, and that also points to the presence of H aggregates, as explained before in the context of this, the spatial correlation or the exciton coherence length. Okay, one can do this Frank-Condon analysis, so empirically also fitting the experimental spectra by taking into account these two expressions for the H and the J aggregates. And these spectra can only be fitted when both the equations for J and H aggregates are used. And now as a function of temperature, one can see that especially this intensity of the 0-0 transition increases as a function of temperature, again indicating the presence of H aggregates in addition to J aggregates. And then finally, one can do a photoluminescence lifetime and fluorescence yield study. So here are the time-correlated single photon counting results, where the IRF is obviously resolved with the different exponential functions. So we managed to resolve two fluorescence lifetime components. And if we first consider the solution, so there's a short lifetime component and a longer lifetime component. So as motivated before, the long lifetime component is more likely related to H aggregates because of the symmetry forbidden transition, whereas the short lifetime is related to J aggregates. Now, when films were formed by means of spin coating, the respective lifetimes remained basically the same, but the relative amplitudes changed, which means that there were many more of the products of the long lifetime component formed. In other words, more H aggregates were formed. Okay, so this is quite an interesting result, that the formation of the film led to molecular ordering, forming more H aggregates, whereas in a solution, it's a much more random orientation. Okay, and then the quantum yield was relatively low, pointing more towards H aggregates than J aggregates. Okay, so as I've illustrated, there are different ways in which we can differentiate between these two fundamental types of parallel dipoles, H aggregates and J aggregates. Okay, let's now move on to the last topic for this lecture, and that is when we consider weak intermolecular coupling. And that is the case when our interaction potential is either much smaller than the energy difference between the two excited states, or our two excitonic states, or the interaction potential is much smaller than the electron-phonon coupling. So in other words, how strongly the excited state is coupled to vibrational modes of the molecules or in the environment. Okay, so we have an excited state wave function, which is given by this expression. In this case of weak intermolecular coupling, okay, we still have these two possibilities, but we have to consider them as separate terms. Okay, so with the energy either localized on one molecule or on the other molecule. So we don't really consider the superposition between these two states as we did in the case of the strong intermolecular coupling forming the excitonic state. These are now two distinct states that still couple through the intermolecular coupling, but this coupling gives rise to resonance energy transfer, as I'm going to show you now. Okay, so in this regime where we have the weak intermolecular coupling, that's called the Förster regime, because Förster was the person who worked out the underlying theory. This gives rise to localized excited states and excitation energy transfer by means of resonance hopping. Okay, so let's have a look into that. Our interaction potential, the one which we have seen before, okay, this implies energy transfer. If we look at this, and we have energy transfer from the molecule 1, which is excited, to molecule 2, which is excited. Okay, so what is the timescale of this excitation energy transfer? If we have to work with a time-dependent process, we obviously have to revert back to time-dependent perturbation theory. But this is exactly what we did in the first lecture. So we use time-dependent perturbation theory to determine the probability of a transition from one state to another state. And this was the equation that was given. But we can use the exact same expression to determine probability of a transition from molecule 1 to molecule 2. Although these states are from different molecules, they are still distinct states, and we consider the probability of the energy transfer. So let's consider two such molecules, molecule A and molecule B. So that was the corresponding graph that was related to this probability of a transition close to the resonance frequency omega naught. Okay, so in this case, we're now considering energy transfer from molecule A to molecule B. And in general, or because of the different factors leading to line broadening, we have to consider energy bands. Okay, so we have an energy band around the excited state of molecule A, and an energy band in the excited state of molecule B. Okay, actually, this picture is not entirely right, because what happens here is actually that molecule A gets de-excited and simultaneously molecule B gets excited. Okay, and this de-excitation and excitation must be in resonance. In other words, we deal with the same delta E, the same energy difference between these states. Okay, because of the energy bands we are considering, we have to consider the density of states. Okay, so here it is depicted in terms of the different vibrational levels, okay, that can simultaneously be de-excited de-excited for molecule A and excited for molecule B. Okay, well, the density of states gives you the number of simultaneous emission absorption combinations that conserve the energy. Or to state it differently, it's the number of combinations of, if we consider this to be the donor that donates the energy to the acceptor, molecule B. So it's a number of combinations where the donor is excited and A is in a ground state, and the donor in the ground state and A excited. So exactly what we have here. So this number of combinations that are available for exchange of the excitation energy and those that conserve the energy. Okay, so the energy differences must be the same. So this gives us the density state. Okay, so this probability of energy transfer must now be replaced with an energy density. Okay, and this is the energy density here given between energy level E and E plus dE. And we have to consider a band of energies. So we consider band of energies around EB, so energy level of molecule B, delta E over 2. So yeah, EB minus delta E over 2, EB plus delta E over 2, just to consider the whole band of molecule B. And if we integrate over this whole band of energies, we get to this expression. So a much simpler expression than we started off with. And now if we make T long enough to make sure that this transition has taken place, then the transition rate, so the rate of the transition of the energy, or actually the rate of energy transfer from molecule A to molecule B, is just a time derivative of this probability, and it is given like that by this expression. Okay, this is an important expression. It's known as Fermi's golden rule. We can use a slightly different expression, which is actually more commonly used. If we also include off-resonance transitions. And now if we switch to donor-acceptor notation, so instead of considering the transition from molecule A to B, we consider energy transfer from the donor to the acceptor, and then we get this expression here. Or if we replace H bar with H over 2 pi, we get this expression here on the right. Okay, so this is a more common form of Fermi's golden rule. Now, we want to know what is VDA, so this coupling potential. And so we want to derive an expression for this, and we also want to derive an expression for the energy density. Okay, so let's first have a look at this spectral, the interaction between the two molecules. So in this case, we again make use of a dipole-dipole coupling, or specifically the transition dipole coupling. Okay, so we are making use of this expression that we used before. And yeah, I'm just using Gaussian units now just to simplify the notation a little bit. And I've also introduced F here, which is called the Lorentz factor. And this factor is a measure of how much the environment shields a charge. Okay, so we have a full charge density and we are in an environment, not in vacuum. So we have to consider how all these charges are being shielded by the environment. If we consider an interaction with another charge density. So in other words, it's a local field correction factor. Kappa here is the so-called orientation factor, okay, which is shown here. If we consider these two dipoles, say dipole of the donor, dipole of the acceptor, and then we have the position vector coupling these two. And actually, this is not drawn exactly correctly because this transition, the position vector connecting these two must be from the midpoint of the donor to the midpoint of the acceptor. But in any case, this graphic shows you the different angles that are at stake here. So theta t here is the angle here on the most left. So that is the angle between the two dipoles, right? And then theta d is the angle between the dipole of the donor and the position vector connecting the two. Theta a is the same for the acceptor. Okay, so this is the dipole orientation factor that we must also take into account. Right, so if we do that, let me see, okay, so then we take the the interaction potential between the donor and acceptor squared, and that gives you basically this one squared. And here you can already see the 1 over R6 dependence, which is a very well-known characteristic of first resonance energy transfer. Okay, let's now consider the density of states. So this is what I've shown you before. We are considering the number of some simultaneous emission absorption combinations. In other words, what we are considering here is the overlap between the fluorescence spectrum of molecule A and the absorption spectrum of molecule B. So we are considering the overlap here, which is shown there. Okay, this spectral overlap that determines the spectral density is proportional to this. Okay, so what I have here is the just integrating over the fluorescence spectrum and the absorption spectrum. So FD is the fluorescence spectrum of the donor, and we make use of the extinction coefficient of the acceptor. Okay, and then we are integrating over all frequencies. So in other words, we are now with this expression exactly considering this overlap. Okay, so our fluorescence spectrum is given by this, where we have included a Boltzmann factor, and we have the Frank-Condon factor. Okay, the Frank-Condon factor is given by the overlap between these two vibrations. Okay, so we have the vibrational states in the excited state, that's our initial state. We consider how much it overlaps with the corresponding vibrational state in the ground state. Okay, so in other words, we are subtracting one vibrational photon from the initial state to the final state. A21 here is our Einstein coefficient for emission, the one that we have derived in the first lecture. Okay, and it's given by this expression here, where I've again using Gaussian units just to simplify. Okay, so this prefactor we have derived in the first lecture. Okay, so this is now our expression for the fluorescence spectrum, but this is in vacuum. Now we want to switch to a medium, in which case we have to multiply with this prefactor, the Lorentz factor squared times the refractive index of the medium. Okay, so this is FD, our fluorescence spectrum of the donor. Let's now consider the absorption spectrum of the acceptor. Okay, it is given by this expression where we again take into account the Boltzmann factor, okay, and the Frank-Condon factor for the absorption. And we again consider Gaussian units. The Frank-Condon factor is given by this expression, where we go from a ground state to a excited state. So we have to include one. Sorry, this is not a vibrational photon that we are including. It is a electronic transition, so an electronic photon. Okay, this prefactor can again be derived from what we have developed in the first lecture. So we start off with the Einstein coefficient for absorption, for which we got an expression in terms of the transition dipole moment, or just a dipole moment in this case. And we also found an expression in terms of the absorption coefficient. The absorption cross-section in this case as a function of the angular frequency. And then we can switch to the extinction coefficient as a function of the angular frequency, and then we can switch to the frequency. Okay, and then we also want to switch from a vacuum state to a state in a medium. So we have to multiply this expression with the Lorentz factor squared divided by the refractive index. Right, so this gives us our the rate of energy transfer from the donor to the acceptor. Okay, so our general expression which we had here with V squared, which we have worked out now. We have worked that out in the previous slide. So you can see here that there's one commonality between what we have developed here for the energy density and for the interaction potential, and that is in both cases we have the dipole moment squared. Okay, so we just have to so what we are doing now is we take these dipole moments from this interaction potential and we put it into this part which is going to model our spectral density. So in other words, it forms part of this integral. So now if we put everything together, the expression for the potential, the interaction potential between the donor and the acceptor, and the energy density, we get to this expression, which is the rate of first resonance energy transfer. Okay, so here we have the so-called first factor, R0 to the power 6, which is given by this. Okay, R is typically given in nanometers, and nu tilde here is the wave number that we are considering in reciprocal centimeters. Kr is the radiative rate of the donor, which we also have derived in the previous slides. Okay, importantly, so this first rate, the rate of resonance energy transfer between a donor and acceptor, depends strongly on, firstly, the relative dipole orientation, okay, which is embedded in this orientation factor. Okay, so the relative orientation between the dipoles, the spectral overlap, which is given here. This is the spectral overlap, and the interdipole distance. And in fact, it has a very strong dependence on the interdipole distance because it scales with R to 1 over R to the 6th. Okay, so this is very often used as a measure to determine the distance between two dipoles. One can, for example, first consider two emitters in isolation, consider their fluorescence quantum yield, and then when they are coupled, the one fluorophore is going to transfer energy to the second fluorophore. So its fluorescence quantum yield or fluorescence intensity is going to decrease due to this coupling, whereas the fluorescence intensity of the acceptor is going to increase. Okay, and this decrease versus increase scales with 1 over R to the 6th. So one can pretty accurately determine the interdipole distance by means of FRET, first resonance energy transfer. Okay, also what is important to note here is that this type of energy transfer is incoherent. The reason for this is during the derivation, when we consider this band of energy, we lost the phase information because we integrated over the whole spectral band of the acceptor in order to get the Fermi's golden rule. Okay, this is in contrast to strong coupling, with which I started this lecture with. The case when we have strong intermolecular coupling forming the excitonic states, you have this continuous transition between the two states, oscillation between the two states. This is a type of coherent energy transfer, and that is going to be the main focus of the next two lectures. Okay, so what we have learned in this lecture is we started with intermolecular interactions, which we developed in the context of electrostatic theory. And then we looked at the case of strong intermolecular coupling or strong dipole-dipole coupling that led to the excitonically coupled dimer system. We looked at two specific types of molecular aggregates or two specific types of dimers, or the H and the J aggregates. I showed you a few examples of how one can discriminate between H and J aggregates based on their particular spectral properties. And I showed you one example of a polymer on which I've worked. And then lastly, we looked at weak intermolecular interactions, and we considered energy transfer, and we developed a theory, and that led to a first resonance energy transfer rate, in which case we consider incoherent resonance energy transfer. Right, so I've set the basis here, developed some basic principles for electronic spectroscopy, and also looked at different types of coupled molecular dipoles in the strong limit and in the weak coupling limit. And all these principles are also setting the base for the next two lectures, which I hope you are not going to miss. They will be given by Dr. Towan Nöthling. He's going to focus on linear and nonlinear spectroscopy, ways to model those spectra, and he's specifically going to look at excitation energy transfer in the strong coupling limit. Okay, thank you very much for listening. You are always welcome to contact me. Here is my email address, also on Twitter, and please feel free to ask any questions. Thank you very much.
Thank you very much, Tjaart, for another very interesting lecture. At the moment, there are no comments in the Q&A, but I'm not sure whether participants would like to raise their virtual hand, and we can give them the opportunity to ask the question in person. Is there any question or comment for Tjaart? Tjaart, nobody is risking to raise the hand. Yeah, let's give them another 30 seconds to think. Please don't be shy. Yeah. Tjaart gave us also already a preview of the next 2 lectures, so maybe also welcome to ask question on the next lectures. Yeah. Tjaart, nobody is risking to ask questions. Then I assume that everybody is happy. Then Tjaart, as you said, your email, you shared your email, and people are welcome to engage with you through an offline channel. And we will still have the meeting, the mini school for 2 weeks, so that there will be still the opportunity. I'm sure you will support morally Towan during his lecture. So if there are still questions for you, people will be able to find you. Yeah. So then thank you very much, everyone. Please don't forget to join again next week. Same link, same time. And I wish you all a good rest of the week. Yeah. Thank you very much. Thank you, Tjaart. Thank you very much for another nice lecture. Thank you.
Yeah, thank you, Francesca, for hosting this. Thank you, everyone, for attending. And please feel free to contact me if you need more time to phrase your question by email. Please feel free to do that. Thank you very much.
Thank you very much. Thank you. All the best. Bye-bye.